talk about torque. Torque is a force, okay, let's talk about torque. You can think of it as a rotational force, okay? Torque causes object to have angular acceleration. Okay. Something that's going at in uniform circular motion does not have a torque applied to it, a net torque, I should say. And we'll talk about Newton's laws and how they apply to this. So something moving at a constant angular speed or angular velocity ends up having no net torque on it. But a torque, you have to apply a torque to get something that's at rest to rotate. Okay, you have to apply a torque to get something that's rotating to stop rotating. So it's very much like an analog to, that just means like a comparison. You can liken it to force, but in the rotational world. Okay, so let's look at what torque is. Torque is caused when we apply a force to an object, but it has to be in a really specific way. Here's the door example. There's a hinge, there's the door. If I want that door to rotate, that's a terrible door, but if I want that door to rotate, I need to push on it, right? Well, if I push in this direction, it doesn't rotate at all. So if I apply a force that goes right through the point of rotation, there's no torque. So I have to have something that goes at some slight angle to that, okay? At least at some slight angle. So the torque needs to pass not through the point of rotation. Force needs to go not through the point of rotation for there to be a torque. And in fact, this is how we define that torque. If I apply a force right here, and I'll just do it like that, there's the force. We find where the point where the force is applied, we can draw a vector from the center of mass, from the point of rotation to where the force is applied. We call that R. And this is our force, and it's a vector. Those are pretty easy to figure out. I mean, those are linear vectors, okay? So we don't get into a mess with that. And then the angle in between them, and it's kind of nice because it almost doesn't matter whether you measure the angle that way or that way or that way or that way. But torque ends up being R times F, so just the magnitudes, times the sine of the angle in between, okay? Right in between. I always like that. Because there are going to be problems where there's a whole bunch of thetas floating around. It's the angle in between the R and the F. So it would be this angle or this angle. Okay, once again, the sine of this angle is the same as the sine of this angle, it's the same as this angle, and the same as the sine as this sine of that angle. So it's really easy to figure out what angle you're talking about if you have those two vectors. Okay, so RF sine of theta. The unit, this is meters, this is newtons. The unit is Newton meters. Okay. Now, what they sometimes say, if you think of this, well, let me redraw. If we think of the door here, and the most efficient way to get that door to close is not to push in this direction or this direction or this direction or this direction. It's to push exactly perpendicular, I'll draw it like that, perpendicular to R. So when the sine is 90 degrees, the angle is 90 degrees, the sine is 1, then it's R times F. We sometimes write this in AP1 as torque equals R perpendicular to F. It's really talking about, if you think of F sine theta, so it's like what part of F is perpendicular to R, what part of R is perpendicular to F. If we think of the perpendicular part, we would be looking for a component. and we're really trying to find how much of F is perpendicular to R. So let's take another look. Let me clean that up a little bit. This is a little tricky, so I want to make sure I got a little room here. So if we think of the part of F that is perpendicular to R as making the thing rotate, okay, then it's a little easier to visualize what component you would want if you broke it down into this. This does it for you, okay? You may never have to break anything up into components in this situation. But let's take a look. If I've got this, let me just make the door right like that, okay? And if I push with a force there, and here's my R, to where the force is applied, right, from my point of rotation, I'll write point of rotation there. It's always nice to define what your point of rotation is, what you're considering your torques relative to. Well, this little thing, if we think of this or this as being the angle in between them, the theta, this would be F sine of theta. This would be F cosine of theta. This force, that component, does no torque. So the part that does contribute to torque is this F sine theta, F sine theta. So there's R times F sine theta. So they sometimes say this F sine theta is the perpendicular part of F. And you can do this a couple of different ways. You can figure out the perpendicular part of R to F. That's a little weird in this situation. Let me show you what that would look like. If we extended F like this, this would be R perpendicular. That's R sine theta, and I'm not going to show you the geometry on that. Oh my God. You really don't have to do this too much, right? If you do have a force, if you can find the direct line to that extended force vector, and we'll do problems where it does that, that's really useful. An example would be, I'm going to do an example right now. Okay, so real quick, I just want to do one final discussion of that equation. Bigger force, more torque. Bigger R, more torque. Closer to perpendicular, more torque. But I want to show you in other physics how this is written. This equation in AP Physics C, for example, is written as R cross F. Okay, the cross means you get the magnitude from the sine of theta, but it's even stronger. This is a vector operation. And remember, vectors have directions, okay? And they're single directions. Left, right, up, down. You can always draw it with an arrow. In AP Physics C, they use what's called the right-hand rule. And I'm just going to demonstrate it for you because you don't need to know it for AP Physics 1. But if I point in the direction of R, and then if my second finger is in the direction of F, my thumb will point in the direction of the torque. Ooh, that's a little weird. Let's do the door. It's weird because it's three-dimensional. So if I have F there and R there, and it's always comical to me to watch students do this. R, F, so the R's in that direction, right? F is down. My thumb points, it's hard to see it, but my thumb points directly at me. So it's actually in this direction towards me. We would view that as coming out of the board. And coming out of the board, it's like an arrow coming towards you. You see the tip. If it were going into the board, let's do that. If F is like this, then we do R, F. So you got to position your hand, and the thumb would be coming into the board, which is like that. It looks like the arrow going away. You're seeing the feathers. Okay, that's really complicated. It's kind of fun for a physics teacher to watch students trying to line things up and when they're doing problems. There are a couple of ways of doing the right-hand rule. That's actually not the way I learned it. I learned it with moving my fingers in a certain direction, curling my fingers in a certain direction. And I think that's actually a little bit easier, but I wanted to show you how that is. So the true vector is given by the right-hand rule, irrelevant for AP1. In AP1, I would just want you to show if the torque is, for example, if the force is like this and R is like this, you'd say, what direction would this thing rotate if this was the only force on it, if this was the only torque on it? Well, it would rotate in this direction. If you push on the door in that direction, it's going to rotate in that direction. So the torque would be, in this case, clockwise. Okay? Now, what we generally do is we generally assume that counterclockwise is positive. But you can overrule that. If you want to say, hey, everything's rotating, I'm going to do this, write it down, right? That's part of your frame of reference. So clockwise and counterclockwise, and I'll sometimes write them as CW or CCW, are the only directions you really need to worry about in AP Physics 1 for torque.